Welcome and thank you for attending our presentation on the new Mochii ISS National Laboratory facility. I'm Chris Owen, CEO of VOXA, and I'm delighted to share with the microscopy community a hallmark event. Electron microscopy capability has arrived at the International Space Station. Team VOXA is a young company based out of Seattle, Washington, with a multidisciplinary focus on automation technologies for advanced imaging. Mochii ISS National Laboratory was created in partnership with NASA Johnson Space Center. The Mochii project aligns with the International Space Station's intended purpose to provide science, technologies, and exploration with benefits to all humankind. In 2013, Italian astronaut Luca Parmitano was performing a routine extravehicular activity outside the International Space Station when his helmet suddenly started flooding with water. After hurriedly bringing Luca into the airlock and back to safety, ISS crew members disassembled the suit and discovered a fan pump separator had been clogged with white particles of unknown origin, causing water from the backpack to flow into his suit. There was no known source for these particles, as the water in the suit was supposed to be high purity. Root cause analyses were stalled while the suit was still on station, as the composition and hence origin of the particles was unknown. The suit was returned to Earth only 6 months later, after which the white particles were analyzed by SEM and identified as aluminum silicate. The root cause was determined to be contaminated water that had leached silicate compounds during storage, and a precipitation event on orbit had caused the malfunction. During this entire period, spacewalks were suspended and only resumed 17 months later at the end of 2014, after the root cause was found and mitigated. If ISS had an SEM on board at the time, the root cause could have been identified and mitigated in days rather than months, allowing a return to full ISS capabilities, including spacewalks, earlier. At VOXA, we've developed a new portable imager and spectrometer called Mochii for unprecedented in situ diagnostics in science. Mochii combines the best of both light and electron microscopes in the size of a coffee maker. In particular, it can provide nanostructure and material composition identification by way of SEM imaging and energy dispersive X-ray spectroscopy. Mochii weighs less than 15 kilograms and consumes less than 100 watts of power. Due to its portability, it mitigates the need to send samples back, is remotely operable via tablets or phones, and fits in the overhead bin of an airplane. Mochii is just as at home in the lab as it is on vehicles, whether on ocean vessels, oil rigs, or even space vehicles. We've tested Mochii in various environments, ranging from undersea habitats, laboratories, and home kitchens, and we're now working on deployment on the International Space Station as part of a NASA SBIR Phase 3 commercialization agreement. While Mochii is versatile and robust for use in the field, some sample preparation is required depending on the type of investigation. We've developed the field sample prep kit to replicate sample preparation tools in the lab. This kit includes typical tools such as tweezers, cutters, and manipulators, as well as carbon conductive tape, all basic tools needed for SEM analysis out in the field. We've also built an integrated metal coating system that provides evaporative coating of heavy metals such as silver onto the sample for enhanced imaging of non-conductive samples. Here's an example of how Mochii will be used on orbit. The application is started from the home screen in the iPad, and a Mochii is selected and connected to from the selector list. Clicking Explore gives access to the exploration portal, and the image comes into view. Navigation is accomplished through finger gestures from pinching, zooming, and panning. The image can be focused using a focus window, which allows focusing and astigmatism to tune up the image quality for maximum sharpness. A sharp image is now in view, and certain analyses can be done, such as measurement using the ruler tool, as well as energy dispersive X-ray spectroscopy. In this case, point spectroscopy of this small particle. The spectrum can be explored and peaks identified. And here we can see that there's good resolution of the light elements, carbon, nitrogen, and oxygen, as well as heavier elements. The analysis is saved and also can be annotated using the notes feature, which is seen by all users on their iPads at the same time. The image is saved to the photo stream for future use. And from here we can exit the app and return back to the home screen. In order to certify Mochii for spaceflight, it needed to pass several verification tests to meet on-orbit engineering and safety requirements. In this section, I'll describe some of the main tests that were conducted to ensure compliance with ISS vehicle requirements. For a highly sensitive instrument, mechanical integrity of the optical and electrical system is critical. The hardware was initially tested to engineering quality levels, which provided numerous areas for improvement in the mechanical design for the next iteration. Mochii was subsequently vibe tested at a lower flight acceptance level that met the two-vehicle requirement for both SpaceX Dragon and Northrop Grumman Cygnus spacecraft, shown under the MEFL chart on the right. For this test, we calculated foam thicknesses for appropriate vibration attenuation using a NASA packaging simulator, and fabricated foam to be used for vibe testing. The measurements from the test closely matched the predictions from the simulator, as can be seen in the bottom right-hand curve for one vibe axis, showing that the target attenuation was reached. This test was successful, indicating that Mochii had a high probability of surviving the flight under these packaging and nominal vibration conditions. With numerous equipment on station and broadcasting satellites on orbit, there are many opportunities for interaction and interference. As an emitting piece of hardware, a major requirement for Mochii is EMI and EMC compliance in the radio emitting environment of low Earth orbit. We conducted multiple iterative tests to check for emissions and susceptibility, and found Mochii to have only minor exceedances which we were able to get exception compliance for. A further wireless and wired communications test was required to ensure that Mochii played well with ISS information technology systems, and could connect to both wired and wireless networks and connect to the ground routing through the Huntsville Operational Support Center. The ping times were found to be nominal, and we were able to demonstrate good control of the payload from the ground. A unique impact of operating in low Earth orbit is that our sensitive instrument moves at 17,500 miles per hour through Earth's magnetic field. This has the deleterious effect of potentially shifting the beam during critical analyses, as the ISS orbits through Earth's magnetic field over 16 times a day. To combat this, our team consulted with the European Space Agency to obtain data on how the Earth's field varies spatially and evolves over time, and we designed passive magnetic shielding for Mochii to counteract the effect. We built a special Helmholtz coil apparatus called Monarch to subject the instrument to the orbital magnetic environment varying between 200 and 650 milligauss, and verified function within required limits for all axes. The ISS is quite a noisy place, with many mechanical systems operating nonstop. To protect crew from excessive acoustic levels, Mochii needed to reduce its acoustic output significantly for operation on the ISS. We conducted iterative testing of Mochii's acoustic system, with several revisions evaluated at Johnson Space Center's Acoustic Laboratory to reduce Mochii's pumps and fans to a low acoustic noise level. This enabled the payload to operate within the ISS cabin environment continuously 24/7. In preparation for on-orbit use, our team operated Mochii in an underwater habitat under extreme hyperbaric conditions, as we reported last year at M&M. The NEMO mission demonstrated successful use of Mochii in an analog mission environment, with crew members conducting research on samples collected from the underwater environment during extravehicular activities. Off-site collaborators were able to simultaneously analyze those samples from shore. See our late-breaking poster 6 from M&M 2019 for more details on this unique experience. After several years of detailed preparation, Mochii launched to the ISS on the NG-13 mission in February 2020, aboard the Cygnus space vehicle on top of a Northrop Grumman Antares rocket. This mission carried 7,500 pounds of supplies, food, and experiments, including Mochii, destined for the ISS. It was an amazing moment for our team to see a system we designed and built lift off the launch pad on a rocket and be propelled into low Earth orbit at 17,500 miles an hour. The Cygnus was captured a few days later after liftoff by flight engineer Drew Morgan and berthed with the ISS shortly after. On ISS, Mochii is planned to occupy the Japanese experiment module continuously. It is wirelessly controlled by iPad both from vehicle and ground by multiple simultaneous users. So far, the mechanical installation has been completed and the system is currently undergoing bring-up operations. After bring-up and verifications of function, Mochii ISS NL will be available for public use. The next part of the presentation covers applications where Mochii can deliver new capabilities. The first is use on the International Space Station. Mochii is intended to be used for three main purposes aboard ISS. First, as a diagnostic device supporting crew and vehicle safety. Secondly, it will be made available for public use as a national laboratory facility for microgravity research and engineering. Third, it will serve as a platform for future mission research, including for Moon and Mars. Electron microscopy is often used for examination of semiconductors and semiconductor packaging, and for reverse engineering products. This example is a failure analysis investigation we helped a small business to conduct with Mochii. During the time of coronavirus, Many engineers and researchers cannot get into their facilities to use larger laboratory machines regularly. Mochii's ability to go anywhere enables work to continue unimpeded, whether at home or at customer sites in the field. In this investigation, a rugged diode used in a high-speed rotary power generator kept failing, throwing off its Kovar cap under a few thousand Gs and damaging the apparatus spinning at very high RPMs. The investigation using Mochii's spectrum imaging feature indicated copper concentrated at the interface seam, resulting in weakness despite the strong housing components. The likely failure mode was fatigue exacerbated by a segregation of softer metals to the seam. ALH 84001 is a Martian meteorite fragment that was found in Antarctica and whose science was instrumental in the formation of the decades-long Mars rover program. The structures shown here, called carbonate inclusions, have analogs on Earth rocks with biogenic origin, formed through life processes of magnetotactic bacteria. In the late 1990s and early 2000s, there was a great deal of study and speculation about whether these billion-year-old structures in this meteorite could have formed naturally, or only with the assistance of bacteria. SEM and EDS were critical tools for these studies, and one such study from 1996 on a high-end field emission SEM is replicated here using Mochii. The composition of the inclusion as well as its boundary chemistry are well characterized. It's further seen that the modern detector of Mochii has greater sensitivity to light elements such as carbon and nitrogen, which are necessary to support life processes. There's great interest to station an SEM in Antarctica or remote outposts for geological institute studies and to help select geological samples for return. I hope you've enjoyed this presentation. In closing, Voxa is very excited to serve new analytical needs for users in the field. Come visit us at projectvoxa.com and we look forward to conversations with all of you. Thank you very much for listening.